working?
Yes, we can see it. I think we'll have to wait for 1 more minute.
Yep, right.
So recording is still going on. Excellent. Okay, now it's 9 o'clock in UTC +0. So we go ahead. Welcome everybody to our next talk. I'm very proud to announce our next speaker, who is Charles Batty from the University of Oxford. And he's going to talk about a Katznelson-Tzafiri theorem for analytic Besor functions. Please, Charles, the stage is yours.
Well, thank you for that introduction. I'd like to say that I participated in this conference last year. Well, it was in April last year. And then I initially just said I would participate. I wasn't planning to give a talk then. Then I was asked to give a talk, and I thought it would be a 25-minute talk. Then I was asked to give a 50-minute talk, so I gave a 50-minute talk. Now this year, well, in discussion with David Seifert, we agreed that I would give a talk, a 25-minute talk, I thought, on this topic. Now, in fact, this year, I've been asked to make it a 50-minute talk. So it will be. I haven't changed the title or the abstract since that decision for it to be a 50-minute talk was made. So what I'm going to do is to add some background material to this, and also, I hope at the end, to say something about the continuous time case. This talk is going to be mainly about the discrete time case.
A small remark. If you wish, of course, you can send us a new abstract and we will substitute it because we are just now finishing the book of abstracts. So you are welcome. This is a very friendly conference. Please feel free to substitute your abstract if you wish. Sorry.
Yes, anyhow. It so happened that around this time, which was, well, in about November, I think, David and I were working on a survey article on Katznelson-Tzafiri theorem, because I'd been asked to write something for some journal, and that seemed to be the best topic. Now, what happened was that when we were putting that together, we discovered that we could include a new theorem, and that's the one that's referred to in this title here. So the Katznelson-Tzafiri theorem is from 1986. That's when it appeared in a paper of Katznelson and Tzafiri. But it went back in a sense to 1970, when probabilists started looking at something and inventing some what they called 0-2 laws, which were the properties of operators and their powers. And they had some very complicated proofs, and Katznelson and Tzafiri, coming in from sort of analysis side more, investigated the proofs and came up with something much simpler, which is the theorem that's now on the screen. So suppose we have a power-bounded operator on a complex Banach space. All the spaces will be complex here because I want to talk about spectrum. Now, if you have a power-bounded operator, you can, by switching to an equivalent norm, you can convert it into a contraction on the same space, but with an equivalent but different norm. So if you like, you can think of T as being just a contraction. However, at times in this talk, I'll be talking about operators on Hilbert space. And if you make that transformation, you lose the contraction property. So when I talk about contractions on Hilbert spaces, that's really a different thing than power-bounded operators on Hilbert spaces. Anyhow, for the power-bounded operator, the spectrum will be contained in the closed unit disk. And so we look at mainly the unitary part of the spectrum. That's the part of the spectrum of T which is on the unit circle. unit circle is denoted by capital T, so there are rather a lot of T's in this talk. And then the result says, quite simply, that if you have a power-bounded operator and the unitary part of the spectrum is only the point 1, then you get the norm of t to the n, identity minus t, converges to 0 as n goes to infinity. This is a triviality if the unitary part of the spectrum is empty, because then you actually get t to the n converges to 0. So that was enough to cover the probabilist needs. But Katznelson and Tzafiri must have thought about, well, what happens if you have more points in the unitary spectrum? Say, instead of just having 1 there, you had 1 and -1. Well, then, no doubt you could get this with t to the n, identity minus t, identity plus t. The norm of all that would go to 0, and so on. So eventually they came up with a more general theorem, which I'll tell you about in a moment. But first, to tell you about that, just notation, A of D for me will be the so-called disk algebra, the Banach algebra of all continuous functions on the closed unit disk, which are holomorphic on the open disk. This is a Banach algebra in the sup norm taken on the closed disk or the open disk, it doesn't matter which. H infinity of D is the Banach algebra of all bounded holomorphic functions on the open disk with the sup norm. And those boundary functions are well known. Those functions are well known to have a boundary function at almost all points. The boundary functions are radial limits of the function on the boundary, and that exists at almost all points. H infinity will not play much role in this talk. I'll be in A of D almost all the time. The algebra that the Katznelson and Tzafiri actually looked at is neither of those. It's the so-called Wiener algebra. So this is, if you look at all the functions on the unit circle, which have a power series expansion just on the unit circle with sigma a n z to the n, where n can be positive or negative. But the property they want is that the sums of the absolute values of the a-n's is finite. And then that's the so-called norm of G in the Wiener norm. So really, this algebra is just the algebra little l1 under convolutions, but disguised as functions on the unit circle. Then you can look at W plus of D, which is the Banach algebra of holomorphic functions on the unit disk, which have a power series naturally, and but we look at those functions where the sums of the absolute values of the Taylor coefficients is finite, and that's in the Wiener norm. Now, these functions are all contained in A of D, and the embedding is continuous from the Wiener norm to the infinity norm. That's just saying the Wiener norm is bigger than the infinity norm. And the map, if you just restrict the function f to the function on the boundary, that gives you an isometric isomorphism of W plus of D onto the subalgebra of W of T. There's some terminology that comes up here. It comes from harmonic analysis. Suppose you have a function in W of T. It's said to be of spectral synthesis in that algebra with respect to a given closed subset E of the unit circle. That means that there is a sequence of functions, GK, in the algebra, each of which vanishes on a neighborhood of E, but it's a different neighborhood for different Ks. And these functions converge in the W norm to G. So this is an assumption that implies that G vanishes on the set E. The converse is sometimes true. And so a closed subset E is said to be of spectral synthesis for W of t if the converse holds, that is, if every function G in the algebra, which vanishes on E, is of spectral synthesis. So spectral synthesis with respect to a set E is stronger than just vanishing on E. So with that background, we can now state the more general version of the Katznelson-Tzafiri theorem, which appeared in the same paper. So take a power-bounded operator T, take a function in W plus of D with Taylor coefficients of this form, then we can define f of t as the sum of an t to the n's over non-negative n's. And this is a functional calculus for the algebra W plus of D and the operator T. It has the nice properties that f maps to f of t is an algebra homomorphism. It's a bounded algebra homomorphism from Banach algebra W plus of D to the Banach algebra of operators on the space X. So suppose we have a power-bounded operator on any Banach space. Let f be in W plus of D, and assume that you have spectral synthesis for the boundary function in Wt with respect to the unitary spectrum. Then the norm of t to the n f of t tends to 0. The basic version that I gave you before had f of t equals identity minus t, so that's looking at the function f of z is 1 minus z, and this is certainly of spectral synthesis with respect to a single point 1. So this is a corollary of, so the basic theorem is a corollary of this more general theorem. Then some observations. All these observations on this slide appeared in the paper of Katznelson and Tzafiri. The first thing is that in order for the general theorem to be non-trivial, the unitary spectrum must be small enough to contain all the zeros of f on the boundary. Now, f is a holomorphic function, and so if the zero set is at all large, then f would have to be the function 0, which is a trivial case, of course. So that really what we're interested in here is when the unitary spectrum is small, that is, it must be of measure 0 with respect to the vague measure on T for sure. If you have a countable closed subset of T, that set E is a set of spectral synthesis for the algebra we're interested in, and therefore vanishing on E is the same as the function having being of spectral synthesis with respect to E. However, there do exist closed subsets B which have measure 0 and are not of spectral synthesis for W of T. Certain subsets of the Cantor set would do that for you. And finally, there's an observation which the Katznelson-Tzafiri attributed to Bourgain, that if f is in W plus D and it vanishes on a closed set E, then f is of spectral synthesis with respect to E if and only if this holds whenever T is a contraction on any Banach space with sigma u of T contained in E. So f being a spectral synthesis is actually characterized by behavior of that's occurring in the Katznelson-Tzafiri theorem. Now for proofs, well, there are several proofs. Katznelson and Tzafiri gave 2 proofs for the basic theorem. One was a direct proof for the basic theorem involving complex analysis, and the proof of the more general theorem via harmonic analysis. A few years later, Wu gave a proof by what I might call functional analysis, which involves the construction of a limit isometry. That's an isometry on a different Banach space, to which Gelfand's theorem about isometries with spectrum, which is just one, being the identity, can be applied, and that then the result drops out. That's for the basic theorem. There are other proofs in a later survey article by Schill and Tomilov. They give two other proofs, one by Fourier analysis and one by complex analysis. I feel that the proofs in this area fall into three categories: those that are based on complex analysis, those that are based on harmonic analysis, and those that are based on the limit isometry route. But these are not entirely separate from each other. There were some extensions which came along quite quickly after the Katznelson-Tzafiri paper. Firstly, Allen, O'Farrell, and Ransford, who are, well, certainly Allen and Ransford are or were at that time experts in Banach algebras, and they, for example, created theorems where the operators were replaced by elements of Banach algebras. They also allowed some weights in certain places, and they also pointed out some connections with Tiberian theorems, which had a big effect on the direction of my research at the time when I heard Graham Allen talking about that subject. And I then became interested in Tiberian theorems and semigroups. A little later, 4 years later, Estelle, Strauss, and Suakia introduced some different algebras from those of the form W of D, or even those of the form A of D, at least potentially different algebras. And they got some results there. Their results were of the more general type, and their assumptions included spectral synthesis. Now, one of the slightly disappointing things about in this theorem is that you have to look at the question of spectral synthesis at times to make the full use of this, and that's sometimes not obvious whether it holds or not. If your unitary spectrum is a countable set, then it's not a problem. But in general, it is. So it'd be nice to have some other theorems where spectral synthesis does not come in. Now, one possibility is to go from the algebra W plus of D, which is the smallest algebra that one could think of, to the much bigger algebra, disk algebra. And let's forget about the intermediate one for a moment. So an operator T is said to be polynomially bounded if there is a constant C such that the norm of the polynomial in T is less than constant times the H infinity norm phi on the unit disk, P on the unit disk. So this is a property that really is only relevant for operators T that have spectral radius less than or equal to 1. And in fact, the ones, if this property holds, then the operator is power bounded. Now, if you have this inequality, you can extend the map P maps to P of T to a map F maps to F of T. That's because the polynomials are dense in A of D. So being polynomially bounded is equivalent to having an A of D calculus for the operator. An A of D calculus simply means an algebra homomorphism from A of D to L of X such that the constant function 1 is mapped to the identity operator on X, and the identity function Z on the unit disk is mapped to the operator T. Now, in 2 stages, it was pointed out that if T is polynomially bounded, and then you get a version of the Katznelson-Tzafiri theorem where W plus is replaced by the disk algebra, and the assumption of spectral synthesis is relaxed to just vanishing on the unitary spectrum. Then you get the same conclusion, Tn f of t goes to 0. So that's neat, but there are not very many polynomially bounded operators. Clearly, any contraction is polynomially bounded with c equals 1. No, that's not true. So clearly, sorry, I misstated that. If c is equal to 1 here, you get something that's like the von Neumann inequality for Hilbert space contractions. So Hilbert space contractions are examples of polynomially bounded functions. Why does no spectral synthesis occur here? Well, the simple answer to that is that every closed subset of T is a set of spectral synthesis when you replace the W of T algebra by the algebra of C of T, of all continuous functions. And then you don't need the spectral synthesis argument. This theorem was proved in 2 stages. The case when T is polynomially bounded with constant 1 was proved by Estelle, Strauss, and Joachim in the same paper as I mentioned before. The case when T was just polynomially bounded was proved by Kershi and Van Heaven later on. Now, this result does play a role, an important role in something that comes up later. But there are some better results, further results not involving spectral synthesis for operators on Hilbert spaces. Firstly, due to Berkovich, who for a completely non-unitary contraction on Hilbert space, you can define by Nash-Voyage functional calculus f of t for f in h infinity, and then you get the result in that case, where f is now not even in the disk algebra necessarily, but t is a particular type of contraction on Hilbert space. There was a result by Laker for a power-bounded operator on Hilbert space. If f is in W plus and vanishes on the unitary spectrum, then you get the standard result. So that was an improvement on the Hilbert space case, power bounded on Hilbert space case. Also, Mustafayev and Zarabi independently, but published 3 years apart, contained a result which doesn't tell you about convergence to 0, but if you take a contraction on a Hilbert space, let's say with non-empty unitary spectrum, and you take f in A of t, then you can get this formula for the limiting value. This limit exists because t is a contraction, is equal to the maximum value of f on the unitary spectrum. So next I want to talk about analytic Besor functions. So this is a class of functions which have been around in the literature from time to time for various purposes. So I'm defining here the analytic Besor functions on the unit disk, and they're the holomorphic functions on the disk for which there's a less than infinity missing in this line, for which this quantity, this integral from 0 to 1 of the sup of f prime on circles of radius r on angles, on angles of theta, the maximum of f prime is finite. Sorry, this is, I've messed this up. This is the wrong definition. I should be taking the sup over theta of the integral with respect to r. Now, any function for which that integral, the corrected integral, is finite, is uniformly continuous on the unit disk. And so they have an extension to a continuous function on A of D. And the class, the space of these functions forms a Banach algebra in the norm given here. So the quantity given here after correction is not a norm because it's the function, constant function 1 gets mapped to 0. This becomes a norm when we throw this in, and it then has all the properties of a Banach algebra. It sits between W plus of D and A of D. These inclusions are continuous. The biggest norm is the W norm, the B norm is in between, and the infinity norm is the smallest one. And these inclusions are proper. The space of analytic Besor functions can be defined in a different way as the functions in H infinity that have a boundary function that lies in a certain Besor space on the unit circle. The polynomials are dense in B of D. Now, it turns out there's a nice integral formula for f in terms of, well, f prime and so on. So this is a formula that just is satisfied by the functions B of that are in B of D. If the function is in B of D, then, well, the finiteness of the corrected version of this integral implies that this integral here is finite, it's absolutely convergent. So a power-bounded operator T has a bounded B calculus, that means with respect to the algebra B of D, if and only if there exists a constant C such that the norm of P of T is less than C times the B norm of P for all polynomials P. Then, if this holds, you can, again, by continuity and density of the polynomials, you can extend this to a map from F in B of D maps to F of T. And that's what a bounded B calculus is. So in 1982, Pella published papers showing that every power-bounded operator on a Hilbert space has a B calculus, bounded B calculus. In 2005, Witzer showed that any RIT operator on a Banach space has a bounded B calculus. A RIT operator is defined in these two lines. It's an operator whose spectrum is in the closed unit disk, and the resolvent outside that disk satisfies an estimate of this form. So this implies that the only point in the spectrum of T on the unit disk is the point 1. No other point on the unit disk can be in the spectrum. Their proofs and their definitions use the Besov norm approach for the Besov norm for the boundary function being in the Besov space. And so they were working with Besov norms of the boundary functions. They're equivalent to the norm that I described before. But they were using harmonic analysis estimates then to get an estimate of this form for their version of the norm, the B norm. Now, going back a slide to this formula for f of z, when f is an analytic Besor function, we could hope to get f of t by simply replacing all the z's in sight by the operators t. And so we could try to define f of t by this formula, where we've got, well, just f of naught coming in, this is an extra term here. And here I've just replaced the z's by t and then written it in the usual notation for operators. But does this integral make sense? Does it converge? In operator norm, it does converge for RIT operators. The RIT condition here can be reformulated to give an estimate for the norm of this resolvent and its square, and this t in front doesn't matter very much. So for RIT operators, this gives a B calculus. This does not converge in operator norm for contractions on Hilbert space in general. If you put in a vector x, it might help you with convergence, but that's still not enough for contractions on Hilbert space. What you have to do to get it to work is to put in both x and x star in the dual space, which in the Hilbert space case is the same space. So we might try this formula now, which is the same formula as before with x's and x stars included. And we would want this formula to hold for all x in x and for all x in the dual space. Now, this integral is absolutely convergent if t satisfies a certain condition, which is written here, and I hope this condition is correct, unlike previous ones. This I call the DGSF condition. The D stands for discrete, because this is a discrete version of a condition found by Gemilko on part and by Xianfeng in collaboration, independently of Gemilko, which played a role at an earlier stage. And when this holds, then it's pretty easy to verify, first of all, that these integrals are absolutely convergent, and secondly, that this formula makes good sense. So one just has to check this for the functions f of z equals z to the k, turning out to work, and then everything else follows easily. So we now have a sort of formula for the bounded B calculus when it exists. So if T is a bounded operator on the Banach space with spectral radius at most 1, then T has a necessarily unique bounded B calculus if T is power bounded and satisfies the GSF condition, but also the converse is true. If T has a bounded B calculus, then T must have the GSF condition. Now I put a load of names up here because it's slightly tricky to say who discovered this first. So myself and Gemilko and Tomilov have two long papers on the B calculus in the case of generators of bounded semigroups. And we got this theorem in that context, in the first two of those papers. The implication if was in one paper and the only if in another paper. But it was pretty obvious that there would be a discrete version, but we didn't get around to writing it down for a while. And then David Seifert and I, a few months ago, did go through that process because we realized we could prove something else. And we've written a paper on that, which is submitted on Archive. But it turned out that Loris Arnold had beaten us to it because he had also written down the discrete version of the B calculus just by following the steps of myself and Gomulka and Tomilov and converting them. So he did a few other things in his paper as well. Anyhow, if you like to have other descriptions of the B calculus, then you can go from the Taylor series. If F such has a Taylor series of this form, and you know what the decays are, or roughly what they are, then you can take this formula. You can replace T by R of T, where R is slightly less than 1. That makes this series converge in operator norm. And then the DGSF condition is enough to tell you that you get a limit as R tends to 1 from below with convergence in operator norm. Another thing that's useful is that the spectral mapping theorem holds for the B calculus. If T has B calculus, then for every F in B, you get this spectral mapping formula. Now, this is the new result from David Seifert and myself. And that is a Katznelson-Tzafiri theorem for B of D. And it says what you would expect it to say or hope it would say. So if T is power bounded on a Banach space and it has a bounded B calculus, or it satisfies the DGSF condition, whichever you prefer, and you have a function which vanishes on the unitary spectrum, then you get the usual result for Katznelson-Tzafiri theorems. T to the n f of t converges to 0 in operator norm. There's no spectral synthesis involved here. The setup that we have here is B of D is intermediate between W plus and A. And you may remember that in one of the earlier slides, I mentioned that Estelle, Strauss, and Zouakia had considered some certain algebras which were intermediate. But this theorem doesn't seem to fit in their pattern. It's not the type of algebra exactly that they look at as far as we can see. And also, our result does not involve assuming spectral synthesis. How does it work? The proof comes in 3 parts. We use the limit isometry route, and that obtains for us an invertible isometry on a different Banach space, such that the spectrum of that isometry is contained in the unitary spectrum of T, and V has a bounded B calculus. The B calculus, it's very easy to see that the B calculus is inherited on V from the B calculus that T had. So that means that V satisfies DGSF. So that's taking the converse result in the relation between B calculus and DGSF. Now then we can read a paper by Kojuharu and Gamilko in 2008, and we can deduce from that that V is polynomially bounded. I say we read the paper rather than just quoting some result from there, because we actually have to read through the proofs of several of their results and pick out the pieces, certain pieces which tell us this fact. Now, having got that, we can look at the work of Kirsty and Van Nerven that I mentioned before, and just by quoting a lemma in their proof, we can get that this implies, first of all, it implies something very strong about V, and then that tells us that we get this limit. Oh, sorry, that's mistake. Slip of the finger. And that tells us that this limit works in the strong operator topology. Now, this is a feature of the limit isometry, that if you're trying to get things in operator norm, you can usually do it by a device which I now call the standard device of considering as another associated operator, which is either, it could be left multiplication on L of X, or it could be some induced operator on the space of bounded sequences in X. Both of them have this nice property that you can get rid of, you can lift this from the strong operator norm, strong operator convergence to norm convergence. Right, so how much time have I got left? I've got about 8 minutes, I think. So I can say something about C0 semigroups. So there's a space of analytic Besor functions on the right half plane, C+. This space has appeared very occasionally in the literature, but almost nothing had been written about it until the first of the two papers that I mentioned by myself and Gamilko and Tomilov. And this space has very similar properties to the space on the disk for lots of things, but it does have some differences which make life more complicated on the right half plane. First of all, this space is not separable, and related to that, the polynomials are not dense in it, and therefore we had to work quite a lot harder 2 or 3 years ago when we were investigating the space. And then we look at the negative generator A, so of a bounded semigroup. So that means that A has a spectrum in the right half plane. And then there's a GSF condition, which I mentioned before, analogous to the DGSF condition, which is both sufficient and necessary for A to have a bounded B calculus on the right half plane. Now, what about Katznelson-Tzafiri theorems for semigroups? Well, suppose f is the Laplace transform of some function g, which is in L1 of R plus. We can then define an operator which is f of A as by this formula for x is in X. It's just the integral of g times the semigroup from 0 to infinity. And then Estelle, Strauss, and Zuakia in a second paper in 1992, and independently Vu in the same year, showed that when you have A, when you have T of T, which is a bounded semigroup, I mentioned on the screen that T of T is supposed to be a bounded semigroup here, and F and G are as mentioned above. And assume that G is of spectral synthesis in L1 of R with respect to the appropriate parts of R. So this is essentially picking out the part of the spectrum of A which is on the imaginary axis and then just putting it on the real line instead. I hope I've got the sign right here. It's very conceivable that this minus sign shouldn't be here, but I think it is there at the moment. And then one gets to the conclusion that the norm of tt, f of a goes to 0 as t goes to infinity. So this looks like a KT theorem for C0 semigroups, analogous to the general theorem from Katznelson-Tzafiri. I've put here another theorem which I've sort of put a question mark to indicate was I the first person who wrote this theorem down. So far as I'm aware, I'm the first person who wrote it down in a paper in 1990. Suppose in this case that the spectrum of A does not intersect, does not have any points on the imaginary axis. Then you get that the norm of TT A inverse tends to 0. Now, you may for a moment think, oh, well, if the spectrum of A intersect IR being empty should, by the previous result, imply that the norm of TT f of A tends to 0 for any f. But yeah, that is, of course, the case, but you have to be careful here. It's not for any f in the whole of the Besov algebra, for example, because the f's here have to be Laplace transforms of functions in L1 of R plus, and that means they're Fourier transforms of functions. So that means f on the imaginary axis is the Fourier transform of an L1 function, and that means that f vanishes at infinity at both ends of the imaginary axis. So that's why you don't get something which is tells you that TT goes to naught. That certainly wouldn't be true. So to get around that, one would hope that there is a statement of this form. A is the negative generator of a bounded C0 semigroup. We assume it has B calculus, or we assume that GSF holds. Take a function f, which is an analytic Besor function, and assume it vanishes on the imaginary part of the spectrum and at infinity. Then we might hope that the norm of TT f of A goes to 0. Now, what does converge, what does vanish at infinity mean here exactly? Well, it could just mean the topological definition, the usual one. It might need something stronger than that. But we have not been able to prove, David Soft and I have not been able to prove anything of any great interest for this so far. So surprisingly, things get more difficult in this case. We can do some of the steps, but not all of the steps, and the ones that I described before. So then just go back to, well, I seem to have gone the wrong way. No, that's all right. Rates of decay. Now, in April last year, in the conference then, I was talking about rates of decay in the in the theorem that I mentioned before, which is here, that in this theorem at the bottom, how quickly does this converge? and that will depend on the norm of the resolvent on the imaginary axis. So here and on the next slide are two theorems about the rate of convergence in the discrete version. The first one is the so-called M-log theorem, which gives an upper bound for the rate of convergence of t to the n identity minus t in terms of what is almost the inverse of a function m, which monitors the resolvent of t near 1 on the imaginary, on the unit circle. But there's a logarithmic correction that comes in, and that has to be there in general. So this was proved by David Seifert in his thesis, and this was proved by David Seifert and Abraham Ung in Abe's thesis. And this is a better result on Hilbert spaces and corresponds to results in the case of bounded semigroups. And here you get the best possible result when T is a power-bounded operator on the Hilbert space, and M is a function of reciprocally positive increase. That's a weak constraint, very weak constraint. It knocks out a few functions which are very badly behaved. And in this case, there's a slight difference here. There, this just says for any C, these things hold. And as you vary C, the rates of decay may vary. But a function of reciprocally positive increase means that the rates of decay of M inverse C(n) are the same for all C. So we get those estimates as well. And that brings me to the end, pretty much on time, or 1 minute over.
Thank you very much, Charles, for this